Today our topic is coastal protection. Contrary to the cylindrical type structure, large submerged structures is a totally different category whereby the DOL ratios is high. Again, D is the dimension of the structure and L is the wavelength. In this type of structure, the Morrison equation is not valid. And here the form drag is usually negligible, whereas inertia is the dominant force acting on the structures. Example of these include oil storage tanks or caissons, etc. In addition, large submerged structures can cause scattering or diffraction of incident wave around it. Typically, in order to study its behavior, physical model may be preferred in order to properly determine the wave-induced force and pressure distribution on the structure. In this figure, we see example of a large submerged structure, specifically a caisson. This is the side view of a caisson. It is typically made up of rigid walls which is placed into the sea, and so that water is pumped out to create a working space for construction in the sea, for example to build a bridge pier. As you can see in this picture, caisson is large typically compared to the wave field around it, and notice that wave can be reflected or diffracted by the structure itself, which is a behavior which is totally different from the cylindrical type structure where DOL is small. Due to the complexity of the structure and flow-field interaction, large submerged structures are typically modeled using the combination of small amplitude wave theory and potential theory, whereby potential theory assumes that the viscosity of the fluid is not important and surface roughness of the object is also not important, which is the case for a large submerged structures. Here the governing equation for the flow field, the boundary condition, and the linearized equation of motions looks like this. We will not go into further detail on this particular subtopic. Enough to mention that by solving this equation, we should be able to get the time and space dependent pressure distribution of the flow field, which can then be integrated to determine the forces acting on the structure.